Hello, welcome to the third and final video of this video series. In this video, we will be dealing with a constantly stirred tank reactor. Here is all of the specific information that we're given. Some of the important things that we need to know before going into this problem is that we are dealing with a constantly stirred tank reactor, and that it is an exothermic irreversible first order reaction that is going from A to B. So this is a very important sentence that we'll be using throughout our derivation today, as well as noticing that we are given a lot of these values, such as the volume, the density, all of these different values, which will help us out a lot in our derivation. It will be a lot easier. As you can see, finally, two cases are simulated. One where the increased cooling by changing TC from 300 to 290, and then the other one from changing 300 to 305. So, with that being said, let's go ahead and hop onto the whiteboard. Welcome back to the whiteboard. As you can see, I've gone ahead and drawn out our situation a little bit. As you can see, we have this cooler on the outside in purple, surrounding the constantly stirred tank reactor, happening place with a constant volume. We know that what is coming in Q in, the volume is staying constant, so we know that what's coming in out is also call it Q in. Then we know that this is an irreversible first order reaction going from A to B, so we can go ahead and get started to deriving expressions for both the change in concentration of A as well as the change in temperature. So the first thing that we're going to need to do is correlate our values. So what we first, like I first said, that important sentence showing us that is a first order, we can show that thanks to Arrhenius equation, we know what K is, what the value of K is. We know that K is simply equal to K naught times the exponential value of the activation energy, EA, times RT, or divided by RT, right? And however, if you remember in the previous, at the beginning of this video, we have a given value for E over R, which is our activation energy over the constant R. So we can go ahead and replace this for that value over the temperature, right? So that said, we can go ahead and get started and figure out the change in concentration of A, right, with respect to time. The main thing we're going to do here is something we've been doing throughout this whole semester, is that what is the change in concentration is simply what comes in minus what comes out, right? And then, of course, minus what is accumulated, right? What was transferred from A to B in here, right? So we're going to be using this equation to solve for this. However, we're going to multiply this by the volume as that is constant to simplify this expression a bit. So with what's coming in, we have Q in, right, multiplied by the concentration that's going in. Then we're subtracting Q in times CA at any time t, right? And then we have to add, we're going to subtract V times KCA, right? And then, of course, what we can do here is divide both sides by V, and we're going to get our expression for the change in the concentration of A. Of course, I'm going to simplify this to a little bit, so then this becomes change in concentration of A, respect to time, Q in. So this becomes CA in minus CA, and then this, of course, we divide by V, and then this V KCH becomes KCA. Alright, so there is our first equation for the change in concentration. Now we want to figure out the change in temperature, right? And the main thing that we're going to be doing here is we're going to be recalling an old expression that we've been using all through middle school, high school, throughout, and that is the change in enthalpy. You know that the change in enthalpy is simply equal to MCAT, right? Mass M multiplied by the constant C multiplied by delta T. And why am I bringing this up? It is because if we go back to C at our constants, we see that we are given our value C, so we can go ahead and plug that in into this expression. So how are we going to use this in here? Well, let me erase this out, free up some space. So change in T, we already have it. This is our change in T, right? The only thing we need to change is add our mass and our constant C. So we know we have our constant C, right? Multiplied by change in temperature, respect to change in time, delta T. Then all we're missing is our mass. However we look, we don't have our mass. But we do have our density rho, right? So we can go ahead and use that to find our mass, as density times V gives us our mass. So this is MC delta T, MCAT, right? So we have our left side, and now we have to figure out this hand side, right? So what will this be? Well, we're going to be using similar idea as here before. We're of course going to be using initial Qn. And then, however, instead of the concentration, we're dealing with the temperature, right? So it's going to be temperature going in minus temperature, right? Then we're going to add a few things. Of course, we're going to be also using this KCA, so it's just going to be minus KCA, and we're going to multiply V, and then we're going to be using negative delta HR, right? So this just becomes positive, and this negative delta HR, because we're given to it negative into our constants, or from our given. Then we're missing one final part of this equation, and that is plus UA, which is the area multiplied by the potential, and then we won't multiplying that by the change in temperature, right? But we're not going to be using these temperatures. Going to be the difference between the coolant temperature, TC, right? So we're going to have TC minus T, or T minus TC, sorry, right? Because the change in the two. So there we have it. Now we can go ahead and simplify this out by dividing this all over to the right hand side. And I actually just remembered this isn't right. This should be rho CQN, I believe. Right. So if we go out and break this out, we get that dt simply equal to Qn divided by V times the time different times the difference in the temperature, and then this whole thing, we have V, so that goes out, so we just have plus KCA, and the bottom rho C, right, multiplied by negative delta HR, right, and then find this last part, all divided by that, so we get plus UA over rho VC times the change in the temperatures, right? So that being said, there are two expressions that we will be using for our derivations in Python, as well as our expression for our K value. Yes. So with that being said, let's go ahead and hop into Python Collaboratory and start plotting these out and figuring out how these interact with each other. Right. Actually, before we move on, I just noticed that these values should be negative, right? As is the difference, right? That's what's being accumulated, what's going away, right? It's a mistake, but Now these equations are good to go ahead and plot them out in Python. Hello, and welcome back to Collaboratory. So I've gone ahead and imported some of the things that we'll be using. Of course, we'll be making subplots and our solve IVP function. Let's go ahead and run that out. And of course, the first step, as always, we want to put in our givens, our knowns, what we know. So I'm going to go ahead and put this on the side. Right? So we want to put in all parameters. So Q is equal to 100. Liters per minute. Initial concentration. Equal to 1 mole per liter. Initial temperature is equal to 350 degrees Kelvin. The volume is constant at 100 liters. Right? And we know that rho density is equal to 1,000 grams per liter. Then we know our constant C, I'm just going to call that big C, is equal to 0.239 joules per gram Kelvin. Then we have our negative HR, neg HR, 5e to the 4th. Sorry. That is joules per mole. Then we have ER. I'm just going to call it ER for now. Hopefully that'll simplify it. 750 Kelvin. Then we have our K naught, which is equal to 7.2. Alright, so now that we've gone ahead and plugged in all of our initial conditions and all of our givens, we can go ahead and plug in the equations that we derived for, right? So what we want to do, of course, as always, we want to define a function, and as always, I'm just going to call it right-hand side for HS, and where we're going to pass t for the time, and then v is a vector, right? Then we're going to unpack the vector as being we're going to have CA and T in that vector, right? And then we can go ahead and start plugging in all our equations. So we know that VCA is simply equal to Q divided by V that whole thing multiplied by CA in minus CA naught, right? Minus CA. And then that whole thing minus K times CA, right? However, we don't know K yet because we need to plug it in, as we said. We know that it is K naught. K naught, we have value, right? K naught multiplied by NP dot exponential. Right, we want the exponential of negative activation energy, so I'm going to put negative ER divided by T, right? Yes. That's our value for K, so we're all good, and then we have our equation for DCA, Q divided by V multiplied. Okay, so now we can do DT. Okay. This one's a little bit more tricky. For the first one, we have Q divided by V again. That is multiplied by Tn minus T. Right? Times T, then plus we have K times CA, so K times CA. That whole thing divided by rho times C, constant C. Divided by that, multiplied by negative HR. Multiplied by neg HR. Right? So we have this divided by this, the whole thing multiplied by negative HR. Sweet. Right. Okay, and then we can go ahead and subtract this final value, which is UA divided by rho VC divided by rho times V times constant C. Yes. And that whole thing is then multiplied by T minus TC. Make sure this is all correct. Okay, that should be good. So now we can go ahead and return our value, and then what we want to return is an array, right, of the dCAs and dTs, right? Shift enter. Then now we can go ahead and recall our solve IVP function, right? So say solve IVP. Call this solution. Let's solve IVP, and then function, we're going to be using right hand side, right? T end, we're going to use the right hand side. T span, we're going to go 0 to T end. Right? Right hand side rule. Said rule, we want 0 to T end, and we want our why not, it's an array, I believe. Let me see, find that out. The method, remember we want to use Rideau as always, and again we want the dense output to be true, right? So the only thing is what we want our y not to be. Of our CAs, so our CA not, and our T not values, right? That should be good, right? So now all we have to do is go ahead and plot these out. So what I'm going to do is go and copy paste from our previous video. Grab this whole thing just for time's sake. 0 to T end, we're going to make this 500 instead. And then instead of the H plot, we're only using CA plot and T plot. And then it's we have sol.sol. So yeah, let's actually recall this as result, so that knows what that is. T plot, and then instead of 3 columns, we're going to have 2 columns. Right? We can delete this. This is CA plot, column 1, column 2. And then this is CA, right? Yes. Concentration of A. We're doing that in moles per liter. Moles per liter. And then temperature, we're going to do temperature, Kelvin, right? And then we don't need this update. We can go ahead and run this, and we should get our two graphs. There we go. Beautiful. So this is what we're looking. It looks a little bit confusing and intricate. This is the concentration of A, so you can see it kind of very quickly swings back and forth, and the temperature is kind of doing a little bit of the opposite motion, but kind of in the same concept. And you can kind of see how these two correlate with time, and as one goes up, the other as well. And there you have it. There are two graphs for this constantly stirred tank reactor. And I'll see you guys in the next one. Thank you for watching.